everybody, welcome back. Glad y'all had a nice holiday yesterday. I'm going to go over the notes today for Lewis structures for covalent compounds, specifically molecular compounds. But I do want to recap and go back over ionic Lewis structures. And so if you remember back, ionic compounds form between metals and nonmetals. So metals and non-metals. Now, those non-metals tend to gain, and what are they gaining? They're gaining electrons. Where are they getting them? They're getting them from the metals. So the metals will lose electrons, and they actually transfer the electrons over to the non-metals. So metals transfer to the non-metals. And so the electrons will move from the metal to the non-metal. And so it results in ionic charges. The metal, because it's losing, forms the cation. Oops, my bad. And the non-metal will form the anion. Again, these are negatively charged and these are positively charged. Positive cats, right? Cats have paws. Okay, so in looking at these, we should be able to identify that sodium is a metal. Sodium is a metal because it's in group 1, and that means it has one valence electron. So when we draw the Lewis dot structures, the dots around the atom represent the number of valence electrons. So dots equal valence electrons. So how do we find that? Look at the group. And it's specifically the last digit of the group number. So you're going to look at the group number to determine how many valence electrons there are. So valence electrons, remember, in the highest energy level, they're going to be the outside electrons, and they're the ones that are going to interact when these bonds form. And so sodium has one valence electron, which actually makes it less stable. And so it tends to lose that electron when it comes into contact with an electronegative nonmetal. That nonmetal is seeking that electron. And so it transfers seamlessly over from sodium to chlorine and forms this chloride ion and the sodium ion. They are electrostatically attracted, and so it actually forms a formula unit, specifically a compound. And so this will actually form NaCl, or sodium chloride. Next, I have another group 1 element like potassium. Group 1, right? It has one valence electron. That one valence electron will move to the chlorine atom. It will form a positive potassium ion, and it will form a negative chlorine ion, and that actually becomes chloride. So this will become potassium chloride. Now notice, I'm not using mono or di or any of the prefixes that we use when we name molecules. These are ionic compounds, and they only form one type of bond. There's only possible one combination. And so we don't have to use prefixes when it's ionic, but we do use prefixes when it's covalent or molecular. Now, I've also got calcium. Now, calcium is in group 2. That's why I have 2 valence electrons on it. So those 2 electrons tend to move and form a 2+ ion. Now, chlorine can only accept 1. And so it has to bond with 2 chlorine atoms or to form 2 chlorine ions. So notice there's a negative charge here and a negative charge here. That's 2 negative charges that will balance out this 2 positive charge. And so it forms CaCl2. Now, what do I call that? Again, calcium chloride. So that's a review of the last unit. Unit 4. Today, we're going to talk about what happens when a molecule forms. And molecules, remember, are covalently bonded. Let's take a look at that. Now, there's a bunch of instructions on this, and I'm going to simplify it for you. So we use this NASL. I just call it NASL. We use this NASL format. And so what's the gist of it? Well, let me go down here to the very bottom. The N represents how many valence electrons are needed. So needed to complete. No, I don't want to say it like that. Needed for the octet. Now, what's important about that is that I want to know how many electrons in total are needed, not how many I have to add to make an octet. Now, we should know that an octet generally is 8, but there are some elements that don't follow that rule. So again, if you go back up here to the very top where it talks about N is the number of electrons that are needed to complete that octet. So most of the time it is 8, but sometimes it's not. There are exceptions. Some of them you already know. Helium and hydrogen, their octet is really a duet, right? Hydrogen and helium. Helium doesn't bond, so we're going to kind of ignore that. But hydrogen and helium only need 2 valence electrons. They're not going to need 8. There's no room for them. Beryllium is actually going to need 4. Kind of strange, right? Why does it need 4? Well, I'll show you in a moment. Boron and aluminum actually need 6, not 8. So an 8 or an octet is not always 8. So I have this little trick. I actually like it, kind of visualizing it. Hydrogen, beryllium, boron, and aluminum. And notice it's kind of this little stair. Step, 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 right? We've got these stairs or these jumps. So hydrogen has 1, double that, it's 2. Beryllium has 2, and again, where am I getting the 2? Because it's in group 2. It has 2 valence electrons, not 2 electrons, but 2 valence electrons. It has 2. It needs 4, double it. Boron and aluminum, they're in group 13. I look at the last digit, that's 3 valence electrons. And so double that. Boron and aluminum needs 6. So it's 2, 4, 6, and everything else is going to be based on 8. Again, the octet will be 8, except for these that I've highlighted in green. Hydrogen needs 2. Beryllium needs 4. Boron and aluminum need 6. So 2, 4, 6, 8. Got it? 2, 4, 6, and then everything else is 8. All right, so let's go back. Again, the N will represent that special octet, whatever that special number is, not how many you add to reach that octet. A will represent the actual. So A is actual. How many does it actually have? So you look at the group number, and it specifically is the last digit. If that's in my window, it is. Last digit. Now S, you're basically going to subtract. So N minus A. So needed minus actual will tell you how many they have to share. So N minus A equals number of shared. Oops. And finally, NASL, N-A-S-L, L will tell you the leftovers. And how do I find that? Well, I look at these two. Oops. So kind of this funny looking thing there and then there. Subtract and subtract. So N minus A gives you S. A minus S gives you L. So A minus S equals number of leftovers. Now, what's important about these two? So the number of shared and the number of leftovers. These are going to be in the Lewis structure. And so it's important to understand when they're sharing the electrons, they do that through a bond. And so a bond is 2 electrons. So 1 bond equals 2 electrons. So if 1 bond equals 2 electrons, and I have number of electrons shared, I should probably put an E there, number of electrons that are shared, then in actuality it's S divided by 2 equals the number of bonds. Now, the leftover electrons are always going to be in what we call lone pairs. That means they're not bonded. So lone pairs are unbonded electrons. So unbonded. And these also have to be divided because the very name pair means 2 electrons. So the leftovers, so L divided by 2 equals the number of lone pairs. Now, this is a lot easier to understand when you actually do the work. So let's look at that. Let's do some practice problems. So I have an example here, and hopefully you remember how to name this from last week. This would be nitrogen trifluoride. And this one's already done for you. So let's just go back and look at what this means. So I've got nitrogen. This is nitrogen. Yes, this is nitrogen, but this is actually needs. So the needs represents the octet. The actual represents the group / valence. I should put that valence. The shared, so these are shared electrons, and this is the number of bonds. Notice I will divide S by 2 and I will divide L by 2. So shared is N minus A, L is A minus S. So NASL. Now, what does this mean? Well, if I have 8 valence electrons that are needed for the octet in nitrogen and 3 fluorines, which also need 8, this is 8 plus 24, resulting in 32 total electrons that have to be accounted for. But in actuality, there's only 26. Well, how did I get 26? Well, there are 5 valence electrons according to the group number for nitrogen. So if I go look at the group number, it's in group 15, which means it has 5 valence electrons. There are 3 atoms of fluorine. And again, fluorine is in group 17, so it has 7 valence electrons. So 3 times 7 is 21, plus 5 is 26. Now, 26 total electrons is what I actually have. 32 is what I need. So I subtract the 2 to figure out how many we have to share. What that means is that those electrons, those 6 electrons, 32 minus 26 equals 6, those 6 electrons have to be shared between the nitrogen and each of the fluorines. Well, we know that 1 bond equals 2 electrons. And so we're going to divide 6 by 2, and we get 3 bonds. Notice in the diagram, in the Lewis structure, there are 3 bonds noted. Now, to find out how many are left over, well, I have actually 26 electrons, but we're sharing 6. So the difference between the two, again, remember, I subtract N minus A equals S, A minus S equals L, and then I just divide S and L. Oh, Saturday Night Live, haha. No, S and L by 2 to determine how many bonds and how many lone pairs are left. And so if I've done that, I've got 20 leftover electrons. I divide that by 2, I'll get 10 lone pairs. If I divide the 6 shared electrons by 2, again, 2 electrons per bond, then I get 3 bonds. And so I have 3 bonds illustrated. Again, they each contain 2 electrons apiece, right? And I've got 10 lone pairs. There's 1 here, 2, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Notice every element is satisfied. It has its octet. So what am I doing? Up here, this needs 2, 4, 6, 8. Nitrogen has all of its electrons, all of its needs. There's 8. Fluorine also needs 8, and that's for each of these. So here's 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Notice each one of them has 8 electrons. So all 4 atoms satisfy that octet. If I include 1, 2, 3, 4, 4 times 8 is 32. Again, I only have 26, which are accounted for. So there's a bond here, there's a bond here, and there's a bond here. Those bonds represent the shared electrons. 2, 4, 6. 6 electrons. 20 electrons are in lone pairs, sets of 2. Okay? Hopefully that makes some sense. Let's do the same for carbon tetrahydride. So I've got, for my needs, we know that carbon is going to need 8. Hydrogen, though, there are 4 of them, only needs 2. 8 plus 8 is 16. But how many does it actually have? So in terms of actual, carbon is in group 14. So it has 4 valence electrons, and there are 4 hydrogens, but each hydrogen brings only 1 electron with it. So 4 plus 4 is 8. I subtract the 2. I get 16 minus 8. And that means that I have to share 8 electrons between the carbon and the 4 hydrogens. Now, subtract 8 minus 8. There are 0 lone pairs. 0 leftovers. I should say leftovers first because you divide this by 4. Well, then you divide that by 2. Divide that by 2. Again, that's no lone pairs. And 8 divided by 2 is equal to 4 bonds. So N minus A gives you S. A minus S gives you L. Once you have found S and L, then you divide by 2 to determine how many bonds and how many lone pairs. We're going to draw that. This central atom is always the least electronegative. That means that it's going to be the farthest from fluorine. Now, I know hydrogen is much farther from fluorine than carbon, but hydrogen can only form a single bond. So in general, carbon is going to be your central atom most of the time. So I'm going to put carbon at the center, and I'm going to put 4 bonds. And guess what? I have 4 hydrogens that bond accordingly. Now there's no lone pairs. Why are there no lone pairs? Well, because hydrogen only needs 2. And notice, I've already satisfied that. Carbon, on the other hand, needs 8. Remember, each bond, 2, 4, 6, 8, has 8 electrons in total. So each bond has 2 electrons. So I have 4 bonds. That means a total of 8 electrons. Everybody's happy. Now, what's shared? These are shared electrons. And so those 8 electrons are shared in the form of 4 bonds. Let's do the next one, carbon dioxide. It's a little bit more tricky. So I've got carbon. Carbon needs 8. Oxygen also needs 8, but I have 2 of them. So I have to multiply that by 2. That means 16 plus 8, that's a total of 24 electrons. That's how many it needs. Actual. Carbon still only has 4. It's in group 14. Group 14 elements have 4 valence electrons. There are still 2 oxygens, but oxygen's in group 16. So there are 6 electrons in its valence shell. That's 12 plus 4. That makes a total of 16. There are 16 actual electrons that we have to account for. Now, subtract N minus A. I get 24 minus 16, and that equals 8. So there are 8 shared electrons. Then I subtract 16 minus 8, and that also equals 8 electrons. So those are my leftover electrons. Now, when I form a bond, I'm going to have to divide these by 2. So 8 divided by 2 equals 4 bonds. And 8 leftover electrons equals 4 lone pairs. Again, these electrons are always paired up when we put them around in the Lewis structure. It makes it easier to read them and to count them. Now, remember, I said that carbon is going to go at the center most times, and this is also the case here. So I've got carbon and oxygen. Carbon is at the center. Now I have 4 bonds. So I'm actually just going to evenly split them because there's no reason not to. So I have 1, 2, 3, 4. Those are called double bonds. It's not 2 single bonds. It's actually double bonds, and they're actually stronger than a single bond. Now, when I look at these, I'm missing something. I'm missing my lone pair. So there's 8 more electrons I have to add, and I'm going to add them in 4 pairs. So I'll have 1, 2, 3, 4, 5, 6, 7, 8. There's a total of 8 electrons. I have 4 pairs. 1, 2, 3, 4. Easy peasy lemon squeezy. Now let's look at the next one. I've got oxygen. Same idea. Oxygen still needs 8, so 2 times 8 is 16. How many does it actually have? Well, it actually is in group 16, so it actually has 6 valence electrons, and there are 2 of them, so that's a total of 12. 16 minus 12 equals 4 shared electrons. We divide that by 2, and that will equal 2 bonds. I'm going to subtract 12 minus 4. That gives me 8. And I also divide that by 2, and that equals 4 lone pairs. There's no central atom. It's just 2 atoms that are bonded, and there are 2 bonds, so another double bond. And now I have to add the 4 lone pairs. 1, 2, 3, 4, 5, 6, 7, 8. So 2, 4, 6, 8 electrons. 1, 2, 3, 4 lone pairs. Now, again, notice 2, 4, 6, 8. There's my octet. 2, 4, 6, 8. There's my octet. These electrons in the middle are shared. We said that we needed 4 shared electrons. That's what we've done here. Notice on this one, I should have done this each time. Hello. Hey, what's up?